Welcome to Lecture 3 of the FOA lecture series on fiber optics. This time we're going to talk about optical fiber. Within the scope of fiber optic components, the fiber transmits a signal as light. The cable protects the fibers, splices join two fibers permanently, and connectors join fibers to connect to active devices so they can be disconnected for rerouting, testing, and the like. And then there's hardware, which holds everything together. But for this lecture, we're going to focus on optical fiber. Within the optical fiber, the light is transmitted in the core. It's trapped in the core by the optical cladding that surrounds it. On top of that, there's a buffer or a primary coating made out of usually an acrylic plastic that protects the fiber from moisture or damage. This is what we strip off when we prepare the fiber for termination or splicing. Most fibers are all glass, but some fibers have a glass core and plastic cladding, and some are all plastic, the ones we call POF. The secret to how optical fiber works is total internal reflection. You've seen this yourself when you stick a stick down in water and you see it bend. That's caused by the different index of refraction between the water and air. Well, the core of the fiber and the cladding have different indices of refraction, and that is used to reflect light of certain angles to totally trap them in the fiber. The angle at which they're trapped is called the numerical aperture. We divide fibers into two types, multimode and single mode. Multimode fiber has a large core that supports multiple rays, or we call them modes, of light, whereas single mode fiber has a very small core and it supports only one mode of light. Because of the different modes supported in multimode fiber, it tends to have higher attenuation and lower bandwidth than single mode fiber. Multimode fiber is typically used in premises applications for local area networks, data links, security systems, whereas single mode fiber is used for all high-speed, long-distance, outside plant applications. Multimode fiber comes in two types. Step index has a core that's all the same material, so the light or the modes travel in straight lines basically, bouncing from one side of the core to the other. Graded index fiber has a core with varying index of refraction that guides the modes. The light that's traveling in the outside of the core is in a lower index of refraction material and actually travels faster. So it tries to keep all the modes in synchronization throughout the entire fiber. There are different sizes of optical fiber, but the majority of all fiber is glass fiber with 125 micron cladding diameter. That's about 5/1000ths of an inch. There are several different multimode sizes with different core diameters, 50 micron and 62.5 micron being the most popular, although in the past we've had 85 and 100 micron cores. Plastic optical fiber is a very large fiber, about a millimeter in diameter with a very thin cladding, and HCS-PCS fiber has a glass core and a plastic cladding with a core of about 200 microns and a cladding of about 250. The attenuation of the optical fiber is caused by two factors, scattering and absorption. Scattering is an inverse function of the wavelength. In fact, the fourth power of the wavelength. So as you go to longer and longer wavelengths, the amount of scattering goes down. There's also absorption at specific wavelengths, typically caused by the OH radical, which is sort of like water, that is left in the fiber. In fact, we make low water peak fiber that reduces the absorption at those peaks to allow the wavelengths to be used for wavelength division multiplexing. Because the attenuation of the optical fiber is less at longer wavelengths, that's where we tend to use them for transmission. Those longer wavelengths are called infrared light, and it's mostly invisible to the human eye. Since the light in the optical fiber is invisible to your eye, it is a problem. If it is large enough in power to be harmful to your eye, you can't see it. But you can check the power level with a power meter or a digital camera. There's an FOA YouTube video showing you how to use a digital camera to determine if there's light in the fiber. You can see the difference in attenuation in the optical fiber at different wavelengths by looking at typical fiber specs. Multimode fiber, for example, has a loss at 850 nanometers, which is just above the visible, of 3 dB per kilometer, while at 1300 nanometers, it's down to 1 dB per kilometer. Instead of losing half the power per kilometer at 850 nanometers, it loses about 20% per kilometer at 1300 nanometers. You can see the same specification changes occur with single mode fiber. And oh, by the way, these are typical specs. The actual standards sometimes have much higher losses just to make sure that all fibers can meet the minimum specifications. Those are not typical specs. Fiber has extremely good bandwidth, but not infinite. Within multimode fiber, we have two factors, modal dispersion and chromatic dispersion. Modal dispersion is actually caused by the different times it takes each different mode of light to travel down the fiber. In step index fibers, they have much lower bandwidth because it lacks the compensation provided by the graded index core of graded index multimode fiber. Both single mode and multimode fiber suffer from chromatic dispersion. That's caused by the fact that different colors or wavelengths of light have different speeds through the glass core of the fiber. In actuality, the red light travels through the fiber faster than the blue light. So a source that has a very broad spectral width or lots of colors in its spectrum, like an LED, suffers much more chromatic dispersion than does a source with a very narrow wavelength, like a laser. And that's one of the reasons, for example, even in multimode fiber, that VCSELs transmit light much further and faster than LEDs. Long single-mode fibers that are used typically for long-distance telecommunications have other factors that affect dispersion. For example, polarization. Polarization means that the light waves are traveling in different planes in the fiber. It's actually caused by stress on the fiber or the fact that the core of the fiber isn't perfectly round. Polarization mode dispersion is very picky. It can vary with temperature or even wind stress on an aerial cable. It's a very small effect, but it's very important for long fibers operating at 40 to 100 gigabits per second or more. Multimode fiber comes in several different varieties depending on its bandwidth when used with 850 nanometer VCSEL laser sources that are typical of high-speed systems used in premises cabling. Single-mode fiber has lots of different variations too, according to what distance it's going to go, what wavelength it's going to be used at, and how it might be used for wavelength division multiplexing. That is a very complex subject and beyond the scope of this simple lecture. One of the things people often want to know is how fiber is made. Well, it's made from a preform. You take a glass tube or a rod, you deposit material around it and heat that up to shrink it into a solid glass rod, the size of the one you see in the top picture. From a preform like this, you can pull as much as 50 kilometers of optical fiber. The preform is placed in a pulling tower. It's heated up on the end, and the fiber is pulled as a thin strand from that giant preform. The fiber is pulled carefully at a controlled rate and monitored for diameter and tested for strength. As it cools down enough, it's covered with that primary buffer coating we talked about, usually a UV-cured acrylate. The fiber is then spooled up and fully tested to make sure it meets all its specifications. Then those spools are sent to cablers who build it into cable, which is going to be the topic of our next lecture. We're the Fiber Optic Association, the Professional Society of Fiber Optics. We're happy to have you join us for this lecture series on optical fiber and hope you'll enjoy all the lectures and videos on our YouTube channel.